Hello there. In this video, I want to talk about some tricks that I use for mental math. Um, I have noticed, I'm a teacher by trade, and I've noticed throughout my years that there are certain things that students struggle with when it comes to computations. So what I want to cover in this video are little tips and tricks that I've picked up and learned throughout the years that have helped me avoid the calculator. Of course, a calculator is not a bad thing, but it creates a stronger sense of knowledge and identity and confidence when someone can do these computations in their head rather than reaching for a calculator. And then with other things, knowing how to type it into the calculator properly is its own knowledge set. So let's go over some mental math tricks. I'm going to start with this simple computation of 7 minus 12. One of the biggest struggles for my students has always been that they struggle with minuses and negatives. So what I always tell them is 7 minus 12, let's think of this as 12 minus 7. Now, these are not equivalent computations, but I know that 12 minus 7 is equal to 5, okay? Now, if I can know that 12 minus 7 is equal to 5, then I can connect it back that 7 minus 12 will just equal negative 5. And I can, because I'm taking that operation of subtraction and I'm flipping it, which will create the opposite answer as if I did 12 minus 7. Now this goes into a little bit of what you kind of already need to know. You need to know some addition facts. You need to know some subtraction facts. You need to know some multiplication and division facts without reaching for the calculator. So this is a little bit of practice to know this. If you don't have strong facts, you need to be able to perform the addition and subtraction, multiplication, division, longhand algorithms so that you can always do it off to the side. Again, calculator is always easier in that sense, but at the same time, it creates more confidence if you can do it without relying on technology to do it for you. So next one is negative 5 plus negative 6. Again, I often get different answers for a question like this. Is it negative 1? Is it positive 1? Is it negative 11? Is it positive 11? Well, this is where I relate it to what's 5 plus 6. 5 plus 6 is just equal to 11. If I bring in the fact that I'm adding two negative numbers together, 5 plus 6 gives me 11. If I make those both negative, now that I can say that negative 5 plus a negative 6 is negative 11. And if we wanted to think of this, we could say, okay, this is just negative of 5 plus 6, since they're both negative, and that gives us negative 11. Same result. So I always like to think, just imagine you're adding two positives together, but in fact, you're adding two negatives. So whatever answer you get at the end of adding those two positives, just make it negative. And this leads us to our last addition subtraction problem, negative 3 minus 4. Notice I have kept these numbers kind of small. I don't want to overwhelm the video with large details about how we do computation. So negative 3 minus 4. Always know that subtraction is just adding the opposite. So this I can say is equal to negative 3 plus negative 4. This is similar to a problem we just did where we talk about negative 3 plus negative 4 being similar to 3 plus 4. 3 plus 4 is 7. Adding two positives together will give me a positive. Adding two negatives together will give me that similar answer, but as a negative. So to recap that really quickly, when I'm subtracting a larger number from a smaller number, like 7 minus 12, I just flip it around. I think, what's 12 minus 7? And I know that if I create the opposite effect of 7 minus 12, it's going to give me the opposite answer. So 12 minus 5 gives me 5, leads me to the conclusion that 7 minus 12 is negative 5. Once more, subtraction is always adding a negative. And when you're adding two negatives together, that is just like adding two positives, but your end result will be a negative instead of a positive. All right, here's a real quick computational problem for 14 times 12. I know in school throughout our years, we often get familiar with, the 5 times tables, the 7 times tables, but do we ever get used to a 14 or 12 times table? And the answer might be no. So how do we do this in our heads? Well, I like to use the distributive property to help me out with this. So I'm going to split up 14 into 10 plus 4, and I'm just going to multiply by 12. Now, you could do this where you split 12 into 10 plus 2 and distribute the 14. That's up to you. I didn't have any particular rhyme or reason for why I chose this. This is what I just chose. So then we use our distributive property. I know that 10 times 12, that is 120. And then 4 times 12 is 48. And then we can add those together and we get 168. Again, this isn't a process I write out every time I'm doing mental math computations. I am just writing down the process that is going on in my head. And really quickly, if we wanted to see the other option where we split 12 into 10 plus 2, I get 14 times 10. We should know how to multiply by 10. Anytime you're doing that, you're either moving the decimal one place to the right, or if it's a whole number, you're just adding a 0 to the end. So that's 140. And then 14 times 2 is 28, and we can see we get the same answer in 168. Now, from multiplication to exponents, let's talk about some perfect squares. And this is not so much a computational trick as it is just rote memorization. I used to encourage my students, memorize the first 10 perfect squares. So that would be 1 squared, which is just 1. So 1 is a perfect square. 2 squared is 4. So 4 is a perfect square. And then we think through the rest of them. 3 squared is 9. 4 squared. Personally became more comfortable with knowing the perfect squares off the top of my head. I said, okay, let's actually memorize the first 15. So 11 squared is 121. But I'm also a bit of a show-off, so I thought, let's do the first 20. So 16 squared is 256. That is all I have memorized at this point. I know other perfect squares, but they don't fall in that consecutive line. And then for the heck of it, let's memorize some perfect cubes. So 1 cubed is 1. So these are just things that I memorize off the top of my head. We could go into perfect fourths and fifths, but beyond that, it's not really necessary. Let's go into some computational tricks for division. Remember that when you have a fraction, what you see here in all 3 of these examples are what are called complex fractions, okay? And so what we're doing here is we're taking the time to simplify these fractions. Now, the mathematical notation is that we want to simplify whatever the second fraction is. Well, I can simplify this by multiplying by 2. That'll cancel these out. Now, a fraction is a lot like an equation. It's a balanced scale. You have to keep balance. So whatever I do to the bottom, I do to the top. So this is the mathematical process of what we're doing. And I get 2 over 3. But notice whenever we have a complex fraction in which the numerator is 1, all we really have to do is note that this means reciprocal. So your final answer is get rid of the 1 and then just flip the fraction that is in the denominator over, and you'll have your final answer. So 3/2 becomes 2/3. And that's the mathematical notation for that. Likewise, we use the similar situation. We'll multiply by 3 here and 3 here to cancel these 3's. And we get just 2 at the top. We get 12 at the bottom. And then let's go ahead and simplify this to be 1/6. But notice what we have here. What we have here is just taking this denominator and kicking it down to the other denominator. We can combine these denominators together using multiplication. So that's the mental math trick I always look at. I don't write out this process of multiplying top and bottom by 3. Now, this is still a handy process to know because when you get into more advanced forms of math, and it's not as simple as multiplying 3 and 4 together, it helps. And then here's a last one. We got a fraction within a fraction within a fraction. So again, using the process, we'll multiply this by 3. Let me just do 3. multiply this by 3 and this by 5, but once again, what we do to one, we have to do to the other. So I'm going to also multiply this by 5 and this by 3. Okay. So this cancels, and I just wind up with 2 times 5 is 10. And then I get 2 times 3, which is 6. And then we can simplify that to be 5 over 3. Now, the mental math trick here is, I'm going to write it off anew on the separate page. So 2/3 over 2/5. The first thing I notice is that when we do this, we simplify it out a factor of 2. So if you have a factor that is the same in both numerators, meaning the numerator of the denominator and the numerator of the numerator, we can cancel those out. Let's go ahead and do that. And then what we have is 1/3 at the top, and we can employ our trick from the first lesson, which is, or from the first fraction, which is take the reciprocal of 1/5, which is 5 over 1, and just multiply. And we'll get more into multiplying and adding and subtracting fractions in the future. But again, these are just some mental math tricks that I use when I'm simplifying my computations. If you have any questions, leave them in the comments section below. You can click on another video that you find interesting on this channel. Otherwise, click like, subscribe, and have a great day. Thanks for watching.